I'd like to talk about application to more complicated observable, which are correlation function of higher point function, but in a particular limit where we can make some progress, which is related to strong coupling, to the regime where we can make contact with string theory and see eventually if what we are constructing using integrability is consistent with what Basso has been claiming, that is the duality between the gauge theory and the string theory. So this work is based on some this talk is based on some recent work with my student Erkan and with Divina Serman. No, the arrow are not working. Thanks. Okay, so this is just a little bit of motivation to remind you why we are considering n equals to 4, just to try to make it fit slightly within the scope of the workshop, because there isn't really any practice here, I guess, if you think about practice as being QCD. Well, for some people who are doing n equals to 4 on a daily basis, this is actually our practice. It's a kind of laboratory where we experiment ideas and especially some ideas related to integrability. And of course, it's also a way of learning things in general about 4D massless gauge theories. And the reason we like it, of course, is because we have all the symmetries, which allows us to do computation to very high loop order, and also to explore some regime we cannot do otherwise, like strong coupling. And one of the key examples that will be in the background of this talk is the duality with string theory. So the way this freedom we have of thinking about n equals to 4 as a gauge theory, if we like it, so, or as a string theory, if we want to develop some more like two-dimensional picture, which is usually very useful when we think in terms of integrability. And that has led to some remarkable results, some of which Collier has been reviewing. Of course, there is a null story before the quantum spectral curve. There is this bet on that story, and the TBA, the thermodynamic bet on that, which was a sort of precursor of the quantum spectral curve, and which will re-emerge here in this talk in a different form. That's why I am mentioning it. And Collier was asking me to show this picture again in case you do not get the point that you can solve everything. Yes, so, but this is, of course, for the two-point function. It's great, but it's a two-point function, and one of the goals, long-term goal will be to get something similar possibly for higher point function. So for correlation function, three-point function, and so on, which, as you guys know very well, is also very useful for constructing sometimes more measurable quantities like these detectors and so on that you like. Okay, so what do we have to construct a higher point function? Well, we already have quite a few methods, some of which are mainly weak coupling or the strong coupling. And in the middle, we have these techniques which goes by the name of hexagonalization, which in principle should give a solution to the problem of computing correlation function at any coupling, in the planar limit at least, in this theory. So the idea is quite simple in principle to present. It's based on this. It's similar in spirit to the triangulation of surfaces. So if you think about correlation function as being some puncture Riemann surfaces, with a puncture representing, some small cross-string or some vertex operators, if you prefer this terminology, or single trace operators if you are more like a gauge guy. Then the idea is that you get the triangulation by cutting along the contraction, the planar contraction that this operator will develop with each other. Okay, so this is a kind of triangulation that we have in mind here. And the hexagons, they are showing up when we think about these triangles as actually also taking into account the operator on the puncture. And so if we give dimension or some length to this operator, to these punctures, we get that the triangles are becoming hexagons. And this is why it has been renamed hexagonalization. So why do we like this method? Well, we like it because essentially this hexagon form factor, we can compute them, or bootstrap them, if you prefer, at any coupling, which means that in principle, these fundamental ties, this triangle, that we can use to build higher correlator, are in principle completely under control. Okay, so that means that we know them at finite coupling, essentially. The difficulty lies eventually in putting them together. So if you actually want to construct something physical or reasonably interesting, you will have to put these triangles together, like you will do in this picture here for the 4-point function, where you get quite a few triangles. Not really good at seeing how many there are, but there are quite a few. And which in practice involves, when we say gluing, we mean that essentially inserting a complete basis of state along the edges that are shared between two triangles. Okay. So this is the way we glue. This is also the way people glue in general in QFT, by inserting a complete basis of state. Here the state are not the 4-dimensional state of the gauge theory, but they are closer to the 2-dimensional state of the string theory, so they are just parameterization, or if you want fluctuation, excitation of the strings that is stretching, the open string that is stretching between two operators. We call them mirror magnets for some historical reason, but which is linked to the spin chain picture. But this is what we have to do. Okay, so yeah, here are just a few examples in case you didn't get it before to see these hexagons. So the structure constant is perhaps the simplest cases where you have this pair of band diagram, which you can think as a way of encoding all these planar Taft diagrams between 3 operators, which here are also shown as spin chain to put all the information in one picture. And by cutting along the seams of the pair of bands here, you get 2 hexagons. Okay, one in the front, one in the back. The most advanced picture for the 4-point function is due to Schroeder and Thiago, and it is shown over there in some fancy 3D-like view. So in principle, this is enough to complete everything. In practice, as I say, it's quite complicated to put things together. So what people do usually, at least for higher point function, is to consider the simplest possible operators of the theory, which are the half BPS operators. Okay? So these are the higher charge generalization of the conserved current of the theory, stress tensor, and so on, okay? Which are built out of the scalar operators. And the nice thing about them is that we don't have to worry about UV or higher divergences. Everything is finite. Everything is expressible in terms of cross ratios and some sort of polarization vectors, which are taken into account in the choice of the scalar operators. So the gluing in general is very complicated. So there are other quantities that are often under study, which have the topology of a disk. So they are called polygons. So they are just obtained by gluing hexagons together, but just on a disk instead of on a surface. So the physical case will be the surface eventually, at least if you are interested in clustering operators or single trace operators. But this type of construction is also quite useful in order to build your way up to a higher point function. Okay. So this is a simplification, of course, because usually for a given number of points we will have less hexagon involved, or less triangles if you prefer, and so that makes the task of resumming over magnons easier. Okay. So these are toy model for resummation for short. Okay. There is also some very nice interpretation. I say that they are a bit like off-shell quantities, or maybe just intermediate step, but there are also some nice interpretation of them actually as some sort of off-shell scattering amplitudes, or if you prefer, scattering amplitude on a Coulomb branch, which with the Coulomb branch here giving some masses to the external particles. So this is not exactly the scattering amplitude that people compute usually in the theory, like Dixon and collaborators. It is some sort of massive version of it, which is conjectured to be equivalent to this polygon. So there is a sort of duality similar to the, if you are familiar to the null polygonal width on the picture, there is a sort of similar duality here that is expected between these polygons and some sort of scattering amplitudes, which makes them also interesting from this perspective. So the simplest case is the octagon. Maybe Frank will say more about it, I don't know, but this is the case where you take a 4-point function and you imagine taking some sort of large charge limit in such a way that the contraction between 1 and 2, 2 and 3, 3 and 4, 4 and 1 become infinite. So that has the effect from the point of view of integrability to separate the front and the back of the picture. So there is a factorization of sort of the clustering diagrams into 2 open string diagrams, which is achieved here by this large charge limit. That will give you the simplest possible example of this polygon, which is the octagon. So why is it so simple? Because here we just take 2 hexagons together, we glue them along a particular edge, a single edge, and what we get is an object which we can compute at any coupling. And what is particularly nice about it also is that this object ends up being exactly computable. So this is one first evidence that there is structure beyond this construction, so beyond the hexagons, which is only showing up after we take into account this sum over the mirror magnets, which here allows one to express this octagon as a determinant of an exact kernel of Basso kernel. So this is an infinite dimensional, this is a freedom determinant of some operator which is expressed in terms of Basso function. So, well, that's a very nice picture and also very inspiring, but in practice, at the moment at least, it's completely unknown how to generalize it to more complicated setups. So, if you're interested in higher point functions, or if you're actually interested in putting these two octagons together and then they talk to each other, the front and the back, then we don't know how to generalize this picture. This is just way too complicated because, of course, the more cuts we have, the more sums, the more everything. And in practice, we don't know what is the resulting structure. We don't know what is the right way of thinking about these infinite sums and how to deal with them. So supersymmetry is helping a lot in the detailed computation, but there are some bottlenecks like this matrix part of the hexagon form factors, which is extremely difficult to handle. Okay. So that's why in practice people seek simplification to pave the way to more, get some better understanding of what type of overarching structure we could have to handle this sum efficiently. A bit like the QSC is resumming effectively an infinite number of thermal corrections in the usual TBA picture. Here we will be seeking for some resummation techniques that extends this case of the octagon to higher point function. So strong coupling is a regime where we can make progress. So this is a limit where, well, to be precise, the limit I'm interested in is not just strong coupling, it's not the limit of Konishi and so on that Collier was talking about. It's more like the classical limit, where we take simultaneously the charge of the operator or the dimension to be large with the coupling constant. Okay. So this is a regime where, in principle, the correlation function should become equivalent to some classical string problem in ADS. Okay, so some sort of minimal area problem, where you find some surface, you minimize the area with some particular boundary conditions that correspond to your observable. Okay. So this has been a very rich corner of the ADS CFT correspondence, which has led to some of these more striking tests with binding string and BMN limit and so on, if you are familiar with that. So here we would like to apply this philosophy to the case of the hexagonalization and see where it is leading us. And well, the bottom line of all of this is that we will be finding some TBA equations which we can eventually compare and which are also generalizing what has been observed directly on the string theory side, notably by Cayetano and Toledo a few years ago. And I should say that the story is also very similar to, well, very reminiscent of what has been done for the null polygonal Wilson loop, or the scattering amplitude problem, if you prefer, by Pedro and collaborators many years ago. Okay, so here just a summary of the plan of the talk and the earlier construction. So, as I said, there is already a lot of results related to this classical limit. In particular, for structure constants, this has been extensively studied in the past for many types of states. There is a long list of people. I put dots for them. And there is also this computation of the octagon as strong coupling by Frank and Thiel and Pedro, which was also showing the way for the structure that we should be looking at. So what we've been considering here is a case of correlation function in a particular kinematics. So doing the full kinematics, like the full 4D kinematics, end up being too complicated at the moment with hexagonalization. It's just some technical problem, but it's a serious one. So we had to restrict ourselves to some particular regime. But this is already hinting at some universal structures that we hope to be able to generalize eventually, like this Chi system, which I would mention at the end. So I will not bring you through all the steps of the computation. It's quite this is all about 2D and well, okay, so there are some results by Gayotto and Mo and Nixky for the spectral network, but I'm not familiar enough to tell whether it's but there are two different ways of generalizing this. One is based on, doing the kind of things that Pedro and company did for amplitudes using Y system. The other one would be Chi system. I don't know which one is the best. Okay, so, this is a long story to tell in practice because, integrability is always technical. But the bottom line is quite simple. There are only a few ingredients we need to eventually build our way up to the result for higher point function. Essentially, some physics on the simplest case, which is the octagon, which is one cut. It gives one piece of information. Then there are two cuts, which give us the other piece of information. And then there is a little bit of mixing up to get the full thing. So, so the basic case is the case of the octagon with a single cut. So if we ignore the dimension of the operator and we just think from a space-time point of view, it is just a square, which is obtained by doing two triangles. And the main observation here that is made to do the calculation of strong coupling is the fact that there is essentially no interaction among these magnons. So when you go to the strong coupling limit, the first thing that is striking you, that you notice is that these magnons are becoming some sort of free relativistic particle with very little interaction. There is just a subtlety about the fact that these magnons can form bound states, and you get these bound states at threshold that start to mix up with magnons which are integrated without being bound. So there is a little bit of ultra-local interaction coming from this bound state at threshold, which forces you to reorganize the result a little bit. But this is some combinatorial analysis, which is well understood. And when you put all of this together, what you get is that this octagon, or this correlation function of 4 points, is exponentiating, as you would expect from a pure string theory analysis, and controlled by some sort of area or free energy that's scale large with a coupling, square root of lambda, and which takes the form of some free energy of some gas. Okay, so there are essentially 4 flavors in the game here, which are just counting degrees of freedom, for the fluctuation of a string in AES frequency S3, so 2 for AES 3, 2 for S3, and so on. And this Y function here that are showing up in the analysis, they are just encoding the geometry of the problem. So here we are putting 2 triangles together in a particular way, and so there are some geometric data like the cross ratios and so on, which are entering the problem as fugacity or temperature, and they are just reflected in the way, this Y function, which are like Boltzmann weight, if you want, depend on this geometrical data. Okay. So this is what we get from this analysis of Peru and France. What we get by generalizing to the 2-cut case, which will correspond to a 5-point function, is how these magnons or gas of particles on different channel, different cut being different channel if you want to think in terms of OP decomposition. So how this guy will interact with each other. So here, the other simplification is that this interaction is extremely smooth. So it can be treated as something which is relatively weak and not very disturbing so much the initial physics happening on each case separately. And besides, it ends up being entirely reducible to the magnon S matrix. So that means that there is essentially not much to compute here. Everything has been known for decades. We just need to input it correctly in our system to get the final answer. So the important simplifications that I want to stress is that in principle, when these magnons on different cuts interact, there is a huge object, a huge matrix part, which takes into account how this magnon can exchange flavor, which is just collapsing here and becoming diagonal. So instead of having like a big matrix problem to solve and to resum, which is I think the real headache with this hexagon approach, here everything is becoming diagonal, so we just get particles which interact diagonally with each other. So it's a huge simplification compared to what we have in general at finite coupling. So, well, the generalization then it's easy. It's when we have 1, we have 2, then we generalize to everything by putting all this cut together paying attention to the way they interact with each other. So the idea that since these interactions are weak and factorized, we can essentially, construct polyatomic gas, if you want, associated to all these cuts by keeping track of the way they interact with each other pairwisely. And to do that, we need to add some combinatorial data to the diagram, which comes from the quiver diagram. So this is just a way of encoding how magnons are interacting with each other on each tile. So the quiver is associated with a triangulation in a canonical way, so you only need to input some orientation. And as soon as you have an orientation, you can draw some arrows which connect different cuts in this picture or different edges in this triangulation according to this orientation. Okay? And the result, what you get, the oriented diagram, is just what is called the quiver, and we can also represent it more formally by a pairing between some charge. So for every edge, we associate a charge in some space, which is called lattice space, if you want the terminology, the precise terminology. And then we define an antisymmetric pairing on it, which is given by this angle bracket, which is just counting geometrically the number of arrows which are connecting each edge to each other. Okay. So this just defines some information about adjacency, or more precisely sign adjacency of the quiver, which we need to know who is interacting with who and in which order. So anyway, so this, once we have all this ingredient, I'm keeping a lot of technical details here, but thanks to all this simplification that I've mentioned before, we can just recast this hexagon formulation as a partition function for some gas of particles and write it directly as a path integral. Okay, so everything here is known. So the path integral is for some auxiliary field, effective field if you want, which is resumming the excitation, and all the information here. So this is just the potential that was worked out by Pedro and friends, if you want, and the K is the interactions that we just worked out from the two-cut case, and by just putting them together, we obtain what we want. And the saddle point approximation is giving us the TBA equation in the end, which directly reflect these ingredients, which I just reviewed for you. So they are of a canonical type, but if you've never seen them before, they are a bit scary like that, but they are very canonical. The structure is very canonical. And we have in blue these driving terms, which are just encoding the geometry. In red, the kernel, which encodes the way this Y function interacts with each other. The bracket, the pairing is measuring the direction of the interaction. As I mentioned before, it's coming from the quiver diagram. And one point which is a little bit tricky here is coming from the contour of integration. So that is a part actually which is probably condensing all the difficulties in the construction, which is that this kernel here, they have some singularities at coincident rapidities. So when the two magnons have the same rapidity, they start interacting very aggressively with each other. And because of that, we actually have to think about how to integrate this interaction. So if the contour was smooth, that would be the end of the day. We will just proceed numerically or analytically. But because this interaction have divergences, we actually have to resolve them and decide how we want to integrate them. Okay. So the natural path here is to actually take the contour and shift them a little bit in the imaginary direction, such as to avoid the pole. But that this introduces a question of how do we actually decide which contour to shift and in which direction. Okay. How much time do I have? 6? Okay. Anyway, so what I want to emphasize is that this is a very general result, and up to this choice of contour, which has to be done properly, this is going to be the answer to everything. Okay. So for this choice of contour, there are actually some rules. It's not totally arbitrary. So we are trying to construct an object which is a correlation function, which must have definite OP limit. By this I mean that it should reduce properly in the OP limit. And this is essentially dictating how we should integrate things. Okay, so we cannot choose I epsilon if you want in a random manner. We have to choose them in such a way that we pick the right behavior in the OP limit. This is a picture which is meant to show it for the two-cut case, just showing that there are different ways we can scale our variables to go from a 5 to a 4-point function, and depending on how we do it, we will essentially kill a cut entirely, or we will fuse them, and the choice of prescription has to reflect these two options. So the fusing being realized in one way and the removing in another, and this is essentially dictating how we should integrate the two rapidities associated to each cut. Yes. So in the upper line here, you have to pick the pole. In the bottom line, you don't pick the pole. So the contour must be chosen such that you pick in one direction and not in the other. So the pole I'm talking about here, this don't have anything to do with excitation at the moment, but you're on the right tracks. I mean, you will see something like that. Sorry. So anyway, there is a rule, there is a guiding rule in principle that you can use, and in many situations, it's all you need to know. You can just implement it directly on any diagram you want and get the answer. Problem is that it's only consistent. This is essentially deciding an ordering among the contour, and this ordering is only consistent if your quiver is linear. Okay, so the quiver has to be some orientation of some A-type diagram, linking diagram. Otherwise, it would be inconsistent. Okay. So also the ordering is only partial because sometimes you just don't care about the order of the contour if there is no interaction, for instance. So that is answering the question of the ordering in the simpler setup. And if you want to do it in the most general setup, you actually have to go through some more complicated analysis, which has to do with contour permutation. And here's an example of a symmetric triangulation of a hexagon, for instance, with some inner triangle. So as you can see in this case, the quiver has a free cycle. I mean, the quiver is an oriented cycle. So if you try to order the contour in a particular way locally here, whatever the rule you use, you will run into a contradiction at some point. Okay, if, for instance, 1 is above 2, which is above 3, which is above 1, there is something inconsistent. So in order to resolve that, you have to, from the get-go, decide to reorder, for instance, contour 1 and 2 in order to open the way for a consistent ordering of the contour. And as you do that, there is something happening, which is that, so this is perhaps connecting to your question, which is that you will extract this residue of the pole and produce a new excitation. So the bottom line is that if you permute the contour, usually what happens is that you will produce some bound state. Okay, so the reordering of states, or contour, sorry, is equivalent to going from a situation where you get only two fundamental excitations here, gamma 1, gamma 2, to a situation where you will get three excitations, including a bound state of gamma 1 and gamma 2. Okay. So the physics behind that is known as a wall crossing. If you're familiar with N equal to theory, so this is usually what happens. You get some spectrum that jumps when you reorder the system. And the TBA equation is just reflecting this physics. Okay, so here, changing usually the moduli of the theory makes you go from one chamber to another where the spectrum is different. Here, this is a contour that we are manipulating. So manipulating the contour is like operating on the moduli of the system and going from one spectra to one spectrum to another. Okay. So, for instance, if we want to resolve the cyclic issue with inner triangle here, we will have to include a bound state of gamma 1 and gamma 2 in order to get something consistent. Okay. So that is making the description of the system more complicated in general because we cannot read out the information directly from the triangulation. We have to think about how to equip the triangulation with an extra layer, an extra structure, which is this construction of a chamber. But, I would continue about this construction of the chamber, but I mentioned that this is the rest of the information about the TBA, so of course, once we have the solution in a given description, we can compute the the free energy directly by just adding up the contribution from each cut. And there is also a concise way of rewriting this TBA, which is encoding in this Y system. So we'll perhaps talk about it. So the construction of these chambers, as I was saying, is closely related to this wall crossing phenomena. And so there is I will go quickly here because I don't have time, but there is a nice, actually, bijection between our problem and the one addressed by Gayotomo and Nitsky many years ago, which allows essentially to solve all of this problem very systematically. So this is something which is well known in this literature, which is related to this nice work of Kontsevich and Soberman, and this wall crossing formula, which essentially allows you to encode all of this information about the system in a very invariant way in this object, which is called the spectrum generator. So, 1 minute, okay. Okay, so after all of this layer, what you get is a description that you can extend to clustering. So here is, as I say, the building blocks are always going to be the same. The only trickery or difficulty is to find a description in terms of excitation that is consistent with your quiver. And in general, this problem can get relatively hard when you go to actual correlators of your theory, which are like this puncture sphere, because these quivers are quite involved. They have multiple cycles and so on. But there are these techniques again from GMN and company that we can take into account and solve our problem. So at the end of the day, what is quite remarkable is that this hexagon TBA that we derive from, something a priori and related to string theory, end up taking this form, this quite universal form of a chi system. So I do not have time to explain how this is coming about, but this is again all related to this work of Gayoto, Mu, and Nitsky. And in this form, it is then straightforward to compare the result with string theory. So string theory is giving you the result in a way, which is this way, and we were getting it in a different way, but in the end, by using all this framework of GMN, we could make the two agree and match very precisely with each other, which is quite remarkable. So there are a few details here which I will be skipping. But the comparison is working very precisely, I want to stress, with the area of the string eventually obtained by some totally different means, which is by solving some geometrical minimal surface problem in AES, agreeing perfectly with the free energy of this gas of magnons, which I was reviewing. Okay, so here comes my conclusion. So there is this nice regime as strong coupling where we can make a lot of progress with correlation functions. What is quite remarkable too is that we are making contact with this rich mathematical framework built by GMN for the PPA spectra of n equals 2 theory. We also have this nice match with string theory. So there is this question about generalizing to ADS5 times S5 and what is exactly the right structure there. The short answer is we don't know at the moment. It's still very challenging to go beyond the two-dimensional kinematics that we were exploring here. There is also some natural question that comes to mind, which is whether there is any sort of connection between these TBA equations that we are finding here and the ones that were the precursor of the QSC in the spectrum, which was discussed by Kolya. They are quite similar in structure, but in spirit, they are very different. The nature is very different. In the case of the spectrum, there is an actual temperature, so there is something which has to do with thermodynamics, which is coming from the length of the operator interpreted as a circle. In the case of correlators, or equivalently for the Wilson loop picture explored in the past, the TBA is arising more like some sort of saddle point approximation to a multi-channel expansion. Okay, so you imagine you have many sums describing all this decomposition and recombination of states across many channels, and in some limits this is exponentiating and controlled by some sort of saddle point. Okay, and it turns out that the TBA is a structure here to describe this saddle point. So the two are very different in nature, but we may still hope that they have some sort of overlap, and that possible the two structures can be combined together, such as to describe more complicated correlation function like the one for excited or non-BPS operators, for instance. One of the very important questions here to answer is whether this chi-system is universally the same, like the y-system for the spectrum, or if we are going to be dealing with some new beast that no one has seen before. Anyway, there are many other outlooks. I will just give them here because I have a lot of time, yes. Thank you. We are not starting from improved hexagons. We are just need to deal with this prescription. It's not the same problem that we are addressing. So the problem with hexagons that you are mentioning is related to non-BPS states. In n equals to 4 at least. If you go to this twisted world of our friends, it's a bit different, but for n equals to 4, there is a difference between LVPS and non-LVPS. Yeah. When it is LVPS, presumably, or at least it's conjecturally, I believe that there will be no problem at all. Yet we have this ordering issue, which is, again, there is a prescription from the hexagonalization. Yeah, it's not like hexagonalization is not telling us what to do. But in practice, when you try to go to the TBA, you have to come up with some nice implementation of it. Yeah. So somehow this bound state that was described and so on, understanding that would be a way to guide those compactors. True, exactly. It's actually quite interesting because this is a problem which is known from Gaiotto and friends, you know that. So what happens is that you need to go to a particular chamber where you get actually an infinite number of bound states. So there are situations where you get you don't have time to talk about it, but you're getting a spectrum that gets infinite dimensional, and which is accumulating on a particular ray, a BPS ray in the terminology of GMN, which correspond to this wrapping. So most presumably, if you want to go to this limit degenerate case of the puncture sphere where you get the OPE, you may have to deal with these infinite chambers and reconstruct the wrapping correction from there. But they have to be there. In principle, it's complete. And then, let me understand one thing. So, you mentioned why and how. Well, conceptually, I don't know. For me, the Y system relies on a chamber. So you need to give me a set of states. The chi system is purely geometrical. It only cares about the geometry of the triangulation. So I don't need to think about resolving these singularities or whatever. So let me ask the second question. So that you derive a Y system for further expansion. Yeah. Compare with John and Brown to convert it into a type. This is true. Well, the Y system for me, the Y system you get for free. Well, you get for free. Okay. Well. Depends on the chamber. If the chamber is finite, so in the terminology of GMN, if the spectrum is only made out of hypermultiplets, you get finitely many of them, you're done. If you get vector multiplets, you get infinitely many.